Ayubowan, a very good morning to all of you, and we warmly welcome all the invitees, the guests, and the participants of the 18th International Conference on Advances in ICT for Emerging Regions, ICTeR2018. The foreign delegates and keynote speakers, welcome to the Pearl of the Indian Ocean. After a prestigious inauguration ceremony yesterday, we're all ready to share our thoughts, wisdom, and insights in ICT and related disciplines through the conference and the series of workshops. So most probably, the next couple of days are going to be very, very mind-blowing, thought-provoking, and probably brain-racking as well. So let me now brief the proceedings of today. First of all, we have the inaugural keynote by Professor Koichi Yamada on aggregation of epistemic uncertainty. And then we break for tea, and after that, we have 3 parallel sessions. Session 1A is based on natural language processing, and we will have that session 1 here in the V.K. Samaranayaka auditorium, the main auditorium of UCSC. And then we have session 1B on software engineering at the ADMTC seminar room, and session 1C on image processing at the mini auditorium. So after that, we break for lunch, and then we have keynote 2. So all the keynote speakers will speak here at the Professor V.K. Samaranayaka auditorium. So that's right here. So keynote 2 is on relational database technology by Dr. Kevin Seneviratna. And then, once again, 3 parallel sessions. Session 2A is on e-learning, which will be right here in this auditorium. And session 2B on software engineering, that is at the ADMTC seminar room, 3rd floor. So I'll explain more once the keynote is over. And then we have session 2C on natural language processing at the mini auditorium. So once we break for tea after these 3 parallel sessions, then we had our 3rd set of sessions, that is session 3A, natural language processing and text analysis. That is right here at the V.K. Samaranayaka auditorium. And then we have session 3B on machine learning at the ADMTC seminar room, 3rd floor. And session 3C on e-learning and education at the mini auditorium, 2nd floor. So that's how it'll happen today. And now we come to that thought-provoking part that I told you of, the inaugural keynote. Let me introduce the keynote speaker, Professor Koichi Yamada of the Nagaoka University of Technology, Information and Management Systems Engineering, Graduate School of Engineering, Japan. Professor Yamada received his bachelor's in engineering in control engineering in 1978 and his master's and the PhD in systems science in 1980 and 1996 respectively, all from the Tokyo Institute of Technology, Japan. He worked as a research engineer for Mitsubishi Research Institute, and he has also worked at the Digital Equipment Corporation in Japan and the Yamataki Honeywell Company. He also worked as a project leader in the laboratory for international fuzzy engineering research developed by MITI Japan. In 1996, he joined Nagoya University of Technology as an associate professor and is currently a full professor in the Department of Information and Management Systems Engineering. He was a board member of Japan Society for Fuzzy Theory and Intelligent Informatics in 7th, 8th, and 11th terms. His main research interests are automated reasoning, machine learning, knowledge discovery, decision making under uncertainty, and effective engineering. So the first keynote speaker of the day, the speech title goes like Aggregation of Epistemic Uncertainty, Certainty Factors and Possibility Theory. Over to you, Professor Yamada.
Well, thank you very much for the nice introduction. My name is Koichi Yamada from Japan. Okay, before I start my presentation, I'd like to express my thanks to all the committee members of this conference for inviting me to this nice conference. Well, today I'd like to talk about the aggregation of epistemic uncertainty. Well, I'm sorry, the subtitle has been changed, but it is almost same, so please don't mind about it. Well, then I'd like to start. Well, first, I'd like to ask a question. What is epistemic uncertainty? Well, in general, uncertainty could be classified into two groups. One is epistemic uncertainty, and the other is aleatoric uncertainty. Aleatoric uncertainty could be called statistical or objective uncertainty. So it is related to frequency or the rate of frequency. Probability is a theory, basically that deal with aleatoric uncertainty. So what is epistemic uncertainty again? Well, in short, it is cognitive uncertainty caused by our incomplete knowledge or lack of information, and it may be called subjective uncertainty. Let's see some examples of the epistemic uncertainty. The first one is a question about gravity acceleration in this room. I think probably no one knows the exact value of the gravity acceleration in this room, but almost all you can answer this question. It is about 9.8 meter per second. But we have to add the about. It means the answer contains some uncertainty. And also consider a case of murder. The question is whether the suspect arrested is the real murderer or not. As you know, suspect is suspect. You cannot say he or she is guilty or not guilty before a decision is made. So whichever you say, the answer contains some uncertainty. Then, uncertainty contained in the answers like this question, these questions, cannot be represented by frequency, as you know. It is, of course, uncertainty considered as a degree of our belief. Well, then, which uncertainty does probability represent? As I said before, originally probability had been a measure to represent frequency. However, in 1740s in England, Thomas Bayes considered a way to deal with degrees of belief in the framework of probability. So it is called Bayesian probability or subjective probability. Well, please consider some statements as an example. Well, it will rain tomorrow at 50%. Or another one is our team will win tomorrow at 99%. As you know, these figures or percentage are not frequencies because tomorrow will come just once. We cannot make many trials to decide these figures. So they are, of course, our beliefs. Probability can be used both for frequency and also for degrees of belief. We can use it as a aleatoric uncertainty and epistemic uncertainty. Then, let's see some other theories for representing uncertainties. Possibility theory is a theory that is related to an adjective, our word possible. And of course, probability theory is related to another adjective, probability. And we also have a Dempster-Shafer theory of evidence. It is a generalized mathematical theory of evidence or uncertainty in the sense that it contained probability theory and also possibility theory as special cases. If you give a set of constraints to this theory, it shrinks to probability theory. And also, if you give another set of constraints, it shrinks to possibility theory. And the third one is certainty factor. It is a certainty representation employed in Mycin. I think young people don't know this one, but it was a famous expert system or a knowledge-based system developed in 1974. I will talk a bit more about the certainty factor later. Then, fuzzy set theory is a theory to deal with vagueness contained in concepts or words. And rough set theories deal with indiscernibility and approximation due to our limited knowledge or limited information. And the last is multi-value logics. They are logics that can represent the truth values between completely true and completely false. There are so many theories representing uncertainty. And please note, these are all theories to deal with epistemic uncertainty. They don't deal with frequencies. It is amazing, there are so many theories. And I think it suggests there are many aspects in epistemic uncertainty. However, today I'd like to focus on only the degree of beliefs. Well, then what is important for dealing with epistemic uncertainty or degree of belief? Well, I think it is capability to deal with ignorance or the unknown situation. For example, suppose there is a gang group in a small town, and your old friend, for example, Tom, has joined it. One day, a murder happened in the small town, and there was no evidence. There was a perfect evidence that one of the gang members did it. But we don't have any other information. In this case, how do you represent the uncertainty that Tom is a murderer? Of course, this is not a frequency. If you use a probability theory, the probability that Tom is a murderer is probably 1 over n. Of course, n is the number of gang members. But unfortunately, we don't know the number of members, how many members there are. So we cannot give the exact value of probability in this case. In that sense, probability cannot represent the uncertainty of this situation. So how about the case of other theories? In the case of possibility theory, an uncertain situation is represented by a pair of possibilities. Possibility of an event A and the possibility of not event A. In this case, possibility that Tom is a murderer is 1. And the possibility that Tom is not the murderer is also 1. These possibilities say that Tom may be a murderer, but may not be a murderer. It's the situation, the unknown situation we are suffering from, you know. It is exactly expressing the unknown situation. If we use Dempster-Shafer theory of evidence, uncertainty is represented by 2 measures. One is plausibility measure, the other is belief measure. Plausibility that Tom is a murderer is 1, and the belief that Tom is a murderer is 0, in the case of this theory. And the third one is certainty factor model. Certainty factor takes a value between -1 and +1. +1 represents perfect affirmation, and -1 represents perfect negation. And 0 means, of course, it is a unknown situation, or that there is no information. In this example, of course, certainty factor that Tom is a murderer is 0. You know, if one of these theories, you can represent the uncertain situations. However, if you use probability, you cannot represent it. Well, then I'd like to talk aggregation of epistemic uncertainty. In everyday decision making, we frequently gather multiple pieces of uncertain information and aggregate the uncertain information. Suppose, please consider the cases, questions like this, you know, which beach resort shall we go to during the next vacation? Or which job should I choose among the multiple offers? Or which is telling the truth, President Trump or the New York Times? In order to answer these questions, we have to gather multiple informations, but almost all of them are uncertain. So we need to gather the information to answer these questions. Actually, aggregation is one of the most important information processing for epistemic uncertainty. There are many applications that need information aggregation in the field of decision making, affective information processing, Seisan fusion, flexible information retrieval, etc., etc. However, there are only a few theories that provide a standard aggregation function. One of them is a Dempster-Shafer theory of evidence. It has a famous aggregation rule which is called Dempster's rule of combination. This rule combines 2 uncertainties derived from the distinct pieces of evidence. This rule is very famous, and many people there are many papers who studied about it, and also there are many variations. But it is a little bit complicated, and actually you sometimes have to face the computational complexity if you use this theory. So today I'd like to focus more simple one, the certainty factor model. Well, certainty factor was devised and used to represent uncertainty of a hypothesis given some evidence instead of probability. I think elderly people know this theory. It was very famous, actually. But these days, they don't know. Okay? The reason why they devised certainty factor instead of probability is that probability cannot express the unknown situation, as I explained before. And also, there is no standard way to aggregate multiple probability distributions. There are several other reasons, but I think these two are most important ones. And at that time, the certainty factor model was evaluated as practical by many practitioners. I mean, system engineers working in companies. However, it was also criticized very harshly by theoreticians, mainly the scholars or researchers in the universities. They blamed it. It is theoretically wrong. Actually, there was no standard interpretation of certainty factor model in the framework of probability theory. Then, I show you the original definition of certainty factors. Certainty factor of hypothesis H given evidence E is represented like this, CFHE. Of course, the value is between -1 and +1. And this certainty factor was defined using these equations. As you see, it is defined using probabilities, prior probability of the hypothesis and the posterior probability of H given E. So they tried to understand in the framework of probability. But we don't adapt the definition because it was proved that the definition is not consistent with the aggregation function of certainty factors. This is the aggregation function used in the certainty factor model, in the model. Let X be the certainty factor of H given evidence EX, and Y be the certainty factor of H given evidence EY. Then, if both of them are greater than 0 or equal to 0, they are aggregated or combined using the probabilistic sum. If both of them are less than 0, then they are combined in the same way. Then one of them is greater than 0, the other is less than 0. In that case, the third equation is used. Then the aggregated certainty factor Fmxy could be understood as this one. Certainty factor of hypothesis H given evidence Ex and evidence Ey. This aggregation function is commutative and associative. So association results are not dependent on the order of the sequence of the evidence when there are multiple certainty factors. I think this is one of the reasons why practitioners thought it is practical. Not only it is simple. Well, then, in the rest of this presentation, I'd like to discuss a new sound interpretation of certainty factors using possibility theory. In this presentation, I'd like to show that the certainty factor could be is transformable to possibility distribution. And the possibility distribution is also transformable back to the certainty factor. It means that both represent the same uncertainty. After that, I examine the new aggregation functions in the framework of possibility theory. I show you the 4 aggregation functions. And one of them is exactly the same as the one used in the mycin, this one. So I think this gives a theoretical basis to the mycin's aggregation, which had been criticized so long time. Well, before going further, let me explain a bit about possibility theory. A possibility is another scale of measure to measure uncertainty with a value in the unit interval. According to Professor Zade, who passed away last year, he said that essentially humans utilize possibility rather than probability in decision making. And also he said vagueness contained in the natural language is essentially possibilistic. If they are correct, possibility seems appropriate for representing epistemic uncertainty. There are some interesting statements about the possibility and the probability. Professor Zade said a lot of things, and I chose some of them. And what is impossible is improbable. Do you agree with it? Second one is what is possible can be improbable. And what is improbable is not impossible necessarily. A little bit complicated, but I think it's right. And also, Professor Dubois and Pratt, they studied possibility theory very much, and they said what is probable must be possible. This is more simple, I think. So there are some relations between probability and possibility. Actually, according to possibility theory, possibility of event A is always greater than or equal to the probability of event A. Well, this slide shows the axioms and the properties of possibility theory on the left side, and those of probability measures on the right side. As you see, possibility measure is defined in a similar way to probability measure. The only difference is this part, shown in the red lines. Probability of A or B equals the sum of probability A and probability B if A and B are disjoint. In the case of possibility measure, possibility of A or B is the maximum of the possibility A and the possibility B. That's the only difference between two. Of course, there are properties are different. And this page shows that both probability and possibility have distribution functions. And here, distribution functions are shown in the lowercase character, small p and small pi. And measures are written in the uppercase characters. Then you can notice that in this page too, algebraic sum of probability is replaced by maximum operation here. And this equation shows that maximum of all possibilities of the possibility distribution must be 1. It may be said as possibility distribution must be normal. And also, this page shows definitions of conditions and independence. Well, details are different, but both of them have a similar concept and similar definitions. And the algebraic product of the probability here is replaced by mini in the case of possibility theory. Well, then, I'd like to go further. We introduce the opposite hypothesis K to an hypothesis H. And both of hypothesis and the opposite hypothesis satisfies this logical formula. K implies not H, and H implies not K. Please look at this figure and consider which is a murderer, male or female. In this case, hypothesis H represents male and K represents female. And we consider between them, we consider unknown situation between them. So this is the three valued logics. In this case, H or K is not a tautology. Also, not H and not K is not a contradiction. Well, please note that assuming the closed world assumption in the epistemic artificial intelligence, then the assertion of male should be rejected if there is no evidence for male. Of course, the assertion of female should be rejected if there is no evidence for female. That is a closed world assumption. Then, if we have no evidence both for male or female, we have to reject both assertions. So, this one, not male, not female, represent it, we don't know anything about it. Then I introduce a causation event which was proposed by Peng and Rizia a long time ago. And H:E represents an event that evidence E supports hypothesis H. This is defined using these three logical formula. I think you can understand it intuitively. For example, if the evidence E supports hypothesis H, if this is present, then of course E and H should be present. Okay? And if evidence E is absent, of course this must be absent. So these are the semantic understanding of this definition. Okay. We also introduce the causation event for the opposite hypothesis K like this. Then we redefine the hypothesis and opposite hypothesis using this logical formula. Here, EH, this one, represents a set of all pieces of evidence that possibly supports H. And EK, sorry, this is EK, mistake. This is EK. EK is a set of all pieces of evidence that possibly support. Sorry, it is, no problem. This is EH and this is EK. Of course, the EH and the intersection of EH and EK should be empty. This logical formula means hypothesis H is true is equivalent to the statement that at least one of possible pieces of evidence support H. This part represents this sentence. And no possible pieces of evidence support K. This part represents this one. Then, if we take negations of both sides, we can get these logical formula. And if we define D, H, and K like this, these hypotheses satisfies this logical formula I showed before. This one. Well, one more thing I'd like to introduce a new definition. Conditional causation possibility is a possibility that evidence EI support hypothesis H only given the evidence EI. This is shown. Please note that this is an explanation mark. And this means that only EI is present, only evidence EI is present, and others are not. So this is defined like this. Only EI is present, and others are not. Then from these definitions, we can derive this proposition, these propositions. The first equation shows that the possibility that H is true, only given evidence E, this one, is the same as the possibility that the evidence supports the hypothesis, only given the evidence. I think you can understand this intuitively because there is no evidence that supports H other than E. So if H is present, then H is supported by this E. Okay. And also, second one shows that the possibility that H is false, only given E, is that same as the possibility that the evidence does not support hypothesis, only given the evidence. Well, then, here I'd like to show the possibility distribution can be represented by a single value in this interval from -1 to +1. Possibility distribution of hypothesis H given only E is represented by these a pair of possibilities. Possibility of H only given E and its negation. Of course, the maximum of this value must be 1 because the possibility distribution must be normal. Then this possibility distribution could be represented by a single value, here GH, using this equation. And I skip the details, but actually this possibility distribution is restored from this one using these equations. So in short, GH is regarded as a single value of representation of the possibility distribution. So this table shows the relations between GH and possibility distribution. If the GH is 0.3, then possibility distribution is 1 and 0.7. And this could be also transformable to this GH. Then we are ready to define the certainty factors. We define certainty factors like this using the GH. And the GK is the same value of the opposite hypothesis K. Okay. If evidence support hypothesis H, then certainty factor is given by this GH. If evidence support opposite hypothesis K, then certainty factor is given by this value. Then we aggregate the certainty factors based on the possibility theory. Well, I only show the rough procedure and the results. When two certainty factors, x and y, are greater than or equal to 0, in that case, x and y are transformed to these possibility distributions. X is transformed to this, and y is transformed to this and this. Then we calculate the possibility distribution of H given only Ex and Ey, both Ex and Ey, using this proposition. Also, we have to assume some assumptions about the conditional independency. Anyway, we get the result, this one. This is a combined possibility distribution. Then after that, this can be transformed back to the certainty factor. Then we get this one, maximum of x and y. In the case of, in the two certainty factors are less than 0, in that case, it is transformed in the same way like this, and in the similar way, we can get this combined aggregated certainty factor, in this case, minimum. And when one of them is greater than 0, the other is less than 0, in that case, we also calculate the possibility distribution, their possibility distribution, and aggregate them in this way. Then finally transformable back to the certainty factor. The result is this one. Then summing up these three cases, we get the first aggregation function, this one. Well, the possibility distribution obtained in this case, one of them is greater than 0, the other is less than 0. In this case, the obtained possibility distribution was not normal. Other cases, they are all normal. All normal, but only this case is not normal. It is because x and y contradict each other. So if we normalize the distribution, then transform it to certainty factor, we get this aggregation function. The third equation is different. Then, the standard operations used for possibility theory are minimum, maximum, as I said, explained. However, mathematically, it is possible to use other T-norm or T-conorm. T-norm is a mathematically generalized product, and T-conorm is a mathematically generalized sum. If we use algebraic product for T-norm and algebraic sum for T-conorm instead of minimum and maximum, we get these aggregation functions. This is the third one. If we don't normalize the possibility of this case, we get this one. And if we normalize the possibility distribution of this case, we get this one. This is the third one. This is fourth one. And please note that the fourth one is completely the same as the Mysin's aggregation function. So we can say that certainty factor model can be justified if we use the framework of possibility theory instead of probability theory. Well, this table shows the mathematical properties of the four aggregation functions. All of them satisfy commutativity, continuity, and non-monotonicity. However, only the Mysin's aggregation function satisfies the associativity. The others don't. Well, I show you some numerical example. Suppose we get 5 pieces of evidence for a hypothesis H, and they are from 0.3 to minus 0.1. Minus value means the evidence supports the opposite hypothesis. And they are written here. And first we aggregate 0.3 and 0.5. And the results are shown here. Then each of them is combined or aggregated with 0.8. Then results are written here. The final result here is here. As you see, the result of the Mysin's aggregation function is 0.44. On the other hand, others are almost 0. This table shows the aggregation result when the order of the sequence is changed. This shows a combination result in descending order from 0.8 to minus 0.7. And this shows the ascending order from minus 0.7 to plus 0.8. As you see, the result of the Mysin's aggregation functions are all the same, thanks to the associativity, but others don't. As you see, the results, others are affected strongly by the recent information. You know, in here, this is a minus value, and the results are minus values. Then, I'll show you another example. Suppose we have a hypothesis H with a high certainty factor, for example, 0.9 at first. Then opposite hypothesis K with low certainty factor, for example, minus 0.1, is given repeatedly. Here, I assume that the hypothesis H represents a true news. For example, news on the New York Times. In the case, we can give the high certainty factor probably. The opposite hypothesis is a fake news or news on the Facebook or some other SNS. And the contents are opposite. This is repeated 20 times. In this case, how the belief will change. Well, looking at these results, this is a final result. Aggregation without normalization is a first line and the third line are sensitive to the repetitive opposite hypothesis, and values of certainty factor decreases rapidly. The part of this red line, these red lines, this is decreasing rapidly. But in the case of minimax operation, the first line case, this case, the result is bounded by the low certainty factor because it is minimum calculation. While the case of algebraic operation accumulate the certainty factor of opposite hypothesis, it goes to the minus 0.7. The upper table shows that the case where the hypothesis H is given in the middle. And the lower table shows the hypothesis H, the true news is given in the end. Well, from this table, we can say that aggregation with algebraic operations, the third line and fourth line, have an effect to accumulate the low certainty factor. Then this effect is risky in cases where much fake information is repeated. On the other hand, it could be useful when we cannot get the certain direct evidence, but we can get much indirect reliable evidence with low certainty factors. Well, we can say like this from the simulations. When much wrong evidence is contained, it is risky to use algebraic operation because of the accumulation effect of certainty factors. And also it is better to use normalization because decreasing effect of certainty factor by wrong evidence is small. So in short, in situations where there is much wrong evidence or many noises, it is better to use minimax operation with normalization. And in cases where most of reliable evidence has low certainty factors and there is little wrong evidence, aggregation with algebraic operation help us. In short, in applications where most of evidence is indirect with low certainty factors, but it is reliable, it is better to use algebraic operation with normalization. The typical example might be clinical diagnosis. Clinicians usually interviews with patient and a lot of evidence, but almost all of them don't have so high certainty factors, because all of them are taught by the patients. Well, I'm not sure. Time is over. Well, I'd like to show a bit about the study itself. What is the position of this talk in the field of artificial intelligence? This may contain my prejudice, but this is my view. And artificial intelligence could be classified into two groups. These days, it seems that almost it is data science and data engineering. And the goal of data engineering is, of course, to analyze data and find patterns, useful patterns, and develop machines to judge something using the useful patterns. And the machine learning and the knowledge discovery is concluded in this field. I am actually studying in these fields, but also I am interested in this epistemic AI. Originally, I think the goal of artificial intelligence was to investigate the human intelligence and to develop the human-like machine intelligence. So these technologies seems included in this field, epistemic AI. So AI itself is usually classified into symbolic AI and computational AI, because traditionally they believe that intelligence could be realized by languages, symbols, or concepts. But after that, for example, connectionism, fuzzy logic, these kind of things appeared as a computational AI. They calculate the intelligence using numerical values. So epistemic uncertainty could be contained in this group, I think. Well, I'd like to conclude my presentation. Well, epistemic uncertainty was discussed, and it is important, I think it is important in the era of data science, as long as humans, robots have to make decisions based on much uncertain or vague information. And the theories of epistemic uncertainty should be able to deal with ignorance or unknown situation caused by lack of information. And the certainty factor model, it was old model and had been criticized for a long time. It is theoretically wrong, but it was recalled and interpreted newly with possibility theory. And I think the aggregation function can be justified theoretically. And I showed 4 simple aggregation functions of certainty factors were proposed, and the mathematical properties were discussed. That's all. Thank you very much.
Thank you very much, Professor Yamada, for that very interesting session on the aggregation of epistemic uncertainty. And for the felicitation of Professor Yamada, let me cordially invite the director of UCSC, Professor K.P. Hewagamage. Thank you very much. Thank you. Thank you very much.
And thank you for the coming all today.
Yes. I'm very happy to invite me to this conference. Thank you very much.
Thank you, Professor Yamada and Professor Hewagamage.